we're live. Okay. So, expansion work. Okay. There are lots of different ways to talk about work. The simplest definition is just that work is equal to force times distance. In a more complicated way, work is equal to the integral of force across distance. And specifically, it's a path integral because, like I said, work is a path function. It depends on how you get there. So, the problem is that chemicals, we can't really do that with chemicals. We can't do force across distance with chemical reactions. They're not really efficient in that way. So instead, let's talk about pressure. All fluids exert pressure, and a fluid is anything that can flow. It's a gas or a liquid. So the air you're sitting in is a fluid. Fluids will also exert pressure. They'll exert that pressure on the walls of a container, holding the fluid, or on anything submerged in it. You are experiencing about 100,000 pascals of pressure from the air you're submerged in right now. You don't notice it because it's all the time. You're used to it. Also, because you are a greasy bag full of salt water, so the water inside you is pushing back against the air around you. So what the hell is a Pascal? Pressure is force divided by area. So you take a force, you exert it over an area. Okay, and the unit of force is a Newton. The unit of area is the square meter. So 1 Pascal is 1 Newton per square meter. Now a Newton is about the weight of an apple, and a square meter is roughly equivalent to the top of a washing machine. So you take a single apple and you spread it out over the top of an entire washing machine. 1 Pascal of pressure is a very small amount of pressure. Hence, atmospheric pressure is a lot higher than that. It is the equivalent of about 100,000 apples on top of a washing machine. Okay. Now, thank you for that, Wesley. We don't usually work in pascals. Instead, we work in atmospheres. Now, an atmosphere is the average pressure of the atmosphere at sea level, or 101,325 pascals, or 101.325 kilopascals. We also use the unit of the bar from barometric, barometer. It's related to the Latin for pressure, or possibly Greek. I can't remember. Anyway, 1 bar is defined as being exactly 100,000 pascals, and that's a lot more popular for engineers because it's just a nice round number. And thus, 1 atmosphere is equal to 1.01325 bar. Okay. We often work in atmospheres in chemistry, but sometimes we do stuff with pascals. Sometimes you have to, just because the pascal is actually based on the scientific units, whereas an atmosphere is not. So, a little bit of math. What is 0.8293 atmospheres in pascals? Okay. What is 231.1932 kilopascals in atmospheres? And what is this human thing called love? All right, so these are fairly simple conversions. So let's go ahead and hop to it. Okay. I'm going to need this guy. We're also going to need Mr. Calculator. All right, so 1 atmosphere is equal to 101,325 pascals. So 0.8293 atmospheres times, so we have our conversion factor, 101,325 pascals per 1 atmosphere. Okay, so we multiply by 101.325. 101,325, not 101.325. 0.8293 times 101,325. So 0.8293 atmospheres is 84,000. Let's see, 84030 pascals. Okay, so a pascal is just a really small unit. Next up, 231.1932 kilopascals in atmospheres. 231.1932 kilopascals is 231,193.2 pascals. Same conversion factor, just in the other direction. 1 atmosphere is equal to 101,325 pascals. So 231,193.2 divided by 101,325. 2 point. Let's see, 1, 2, 3, 4, 5, 6, 7 sig figs. So 2.281699 atmospheres. And finally, this human thing called love. Fools rush in where angels dare to tread. Okay, so those are just some very straightforward conversions. Atmospheres and pascals. They could very easily ask you to do something like that on a test. All right, moving on. Oops. So, pressure. When you change pressure, that means pressure is equal to force over area. So you're either changing the amount of force you're exerting or you're changing the area it's exerted over. Okay. So if you increase the area, then you are going to decrease the pressure because force is divided by area. Okay, so that's the principle behind snowshoes. They increase the amount of surface that you're standing on so that you can more easily walk over snow because you don't push down into it quite so much. Conversely, a high heel dramatically decreases the amount of surface area, so it's going to dramatically increase the pressure, which is why you have to be careful what kind of surfaces you walk on in heels. You step on, muddy grass in wet grass, a wet lawn, wet dirt ground in boots, you'll probably be okay. You step on a high heel, and you're going to just stab right into it. Okay, the other thing you can do is change the force, change the amount of weight pushing down on that area. Increase the force, you're going to increase the pressure. Decrease the force, you're going to decrease the pressure. Now, let's rearrange. Pressure is equal to force divided by area. So we can turn that around. Force is equal to pressure multiplied by area. Okay. Pressure is newtons per square meter, so you multiply that by square meters, you're left with newtons, you're left with the force. And now we can finally bring this back around to work. Okay? We talk about this in terms of expansion work. Okay? We're talking, again, we're going back to engines, steam engines usually. And that's where all of this stuff started. Work is equal to force times distance. Force is pressure times area. So pressure times area times distance, that's a volume. Okay, so what we're talking about here is, let me bring back this guy. Okay, so we have, a cylinder with a piston in it. The piston is free to move. The piston has a surface, some area. The piston is now free to move in or out. If it moves across some distance, d, then you have changed the volume inside the cylinder. The piston goes in, the volume is going to decrease. The piston goes out, the volume is going to increase. Okay, so that is how we can get work out of a chemical reaction. You heat things up inside here, or you blow things up inside there, it will push the piston out. Okay. So that's how a car engine works. Okay, so when a system expands, it's expanding against some external pressure source, the air. It has to do work in order to expand. Okay, and if the system is doing work, then it is using energy to do that work. Okay, so it's putting energy into the surroundings. So when a system expands, then work is going to be negative because the system is losing the energy to the surroundings. Okay, so if delta V is greater than 0, the system is expanding, it's doing work, so work is going to have a negative value. When the system is compressed by some external pressure source, then it's going to get smaller, and the surroundings are now doing work on the system. So work is going to have a value of greater than 0, which is why work is equal to negative P delta V. Okay? Because, the system is expanding, work has to be negative. When the system is contracting or being compressed, work is going to be positive. Okay? So be very, very careful and don't forget that negative sign. Work is equal to negative P delta V. And remember, physicists reverse this. They get it backwards. That's why we don't like them. Okay, so we're talking about pistons. Okay, this was why thermochemistry was invented. They wanted to make better guns, better bombs, and better choo-choo trains. Okay, so piston moves out, does work. Piston moves in, work is being done. Okay, on the system. So let's talk math. What is the work done by a system that expands from 101.25 mils to 125.75 mils against a constant pressure of 1.225 atmospheres? Is it going to be positive or negative? And what is the final volume if you do 253.5 joules of work on a 2.575 liter system at 1.207 atmospheres? All right. So let's bring up the paper again. Work is negative P delta V. Okay. If you look down at the bottom, you'll see that I provided some conversion factors. 1 atmosphere is equal to 101.325 pascals. 1 liter is equal to 10 to the negative third cubic meters. And 1 liter atmosphere is equal to 101.325 joules. Okay. So these are all different ways of making these conversions so that we can actually do this math. Okay. A liter atmosphere, that is a weird looking unit, but it's just talking about a change in pressure multiplied by volume. And that's all work really is. But in scientific units, it would be pressure in pascals or Newton per square meter and a volume in cubic meters. But frequently in chemistry, we work in liters and atmospheres. It's the exact same thing. Okay, you just have to do the proper conversion factor. So, what is the work done by a system that expands from 101.25 mils going to 125.75 mils? Okay, so this is our change in volume, delta V. Remember, delta is always going to be final minus initial. Okay, whatever your final position is minus whatever your initial position was. Okay, so it's going to be 125.75 milliliters minus 101.25 milliliters. So our change in volume is 24.50 milliliters. Or let's go ahead and convert that to liters, 0.02450 liters. And our pressure was 1.225 atmospheres. So work is negative P delta V is equal to negative 1.225 atmospheres multiplied by our delta V of 0.02450 liters. Going to give us a work value of 1.225 times 0.0245, 0.03001 liter atmospheres, which doesn't make a whole lot of sense. We pretty much never talk about energy or work or anything like that in the units of liter atmospheres. We always talk about it in joules or kilojoules. So we can just go ahead and convert that really quickly because it's 101.325 joules per liter atmosphere. So 3.041 joules. So that's about enough energy to pick up 3 apples off the floor and put them on the counter. Oh, but really quick, is it going to be positive or negative? Because I almost immediately completely neglected this. Boom, boom. Be very careful about your negative signs. Okay, this system is doing work. It's expanding into the surroundings. It is going to be negative. Okay, be very, very paranoid about dropping negative signs. Okay, one time in grad school, I was working on a homework assignment, 5 pages of math. And I knew the answer was coming out wrong, and I kept on redoing it and redoing it, spent hours on it, eventually realized that I was dropping a negative sign on the second page. Annoyed the piss out of me. All right, so that was the first problem. For the second problem, we are doing work on a system. Okay, so our work is equal to positive 253.5 joules. I know it's positive because we're doing work on the system, so we're compressing it. The volume is going to get smaller. The pressure this is happening at is 1.207 atmospheres, and our initial volume is 2.575 liters. Okay. So, what is the final volume going to be? Well, work is negative P delta V is equal to negative P times VF minus VI. So, that means we divide both sides by negative P. VF minus VI is equal to negative work over pressure. And then VF is equal to VI minus work over pressure. Just added the initial volume to each side. So 2.575 liters minus, let's go ahead and convert from joules to liter atmospheres, just to make things easier for this particular problem. It's 1 liter atmosphere is equal to 101.325 joules. So, bring back up Mr. Calculator. 253.5 divided by 101.325. Oops, 325. It's going to be 2.502 liter atmospheres of work. That's 2.502 liter atmospheres divided by 1.207 atmospheres. Now, just being really careful about the sign, okay? The system, we're doing work on the system, so therefore it has to have a positive sign. So minus positive divided by positive. All right, so now 2.502, we divide that by 1.207. And then it's going to be 2.575 minus that. So 2.575 minus 2.073. Meaning our final volume is 0.502 liters. Okay, so we've compressed the heck out of it. We did a lot of work on that system. Okay. You don't have to work in liter atmospheres. You could convert from atmospheres to pascals and liters to cubic meters just as easily. It would just be kind of weird looking. It's always going to be kind of weird looking. But these are some fairly basic, fairly straightforward expansion work problems. Work is negative P delta V. The units of work is measured in joules. Pressure is typically measured in atmospheres, but technically the proper scientific unit is the Pascal. Volume, again, typically we measure that in liters or milliliters, but the proper scientific units are the cubic meter. So there are plenty of conversion factors that you're going to have to memorize. 1 atmosphere is equal to 101,325 pascals is going to be the big one. That's the one you definitely, absolutely have to know. I'm not so certain about bars, but you should go ahead and remember them as well. 1 bar is exactly 100,000 pascals. Okay. I believe that does it for, yes, that does it for our expansion work problems. That does it for this particular set of slides. Chapter 8 is going to be big on math. It's going to be big on these weird abstract concepts. So do not wait until the last minute to learn about Chapter 8. Okay, but that does it for this set of slides. So I'll see you in a few minutes to talk about internal energy. See you then.